Hello everyone. So today I'll be practicing a buffer overflow practice on a vulnerable server called vulnserver. So that server is actually meant for practice and that server has a buffer overflow vulnerability. We will exploit that and gain a reverse shell back to our system so that we can control it remotely. So that is the goal. So for this I'll be running the vuln server on Windows machine, which I'm running as a virtual machine, and we will be debugging. We'll be using the debugger called immunity debugger, and I'll be using Kali for my attack machine. So let me show you how it goes. So this is the Windows virtual machine. I have immunity debugger installed. Run it as an administrator. This screen on which I am actually using this Windows, this is actually sidecar on iPad, so the display size is a bit weird, I know. Let me open the vuln server that is already there on my desktop. Let me open it. I can show you also, it is there. If you go desktop, here you'll get it on GitHub. Search for vuln server, you'll get a GitHub link and download from there. Unzip the zip and you have the stuff here, and just open it in debugger like this. Now it is running, it is there. Sorry, it is not running. It, as you can see in below, it is paused. Maybe I should change my display. I guess it will be it is visible now. Okay, so this is it. It is showing paused, but I'll run it. Give me a minute. Maybe place it somewhere here. Okay, now let me run it. You just have to play the play button for it to be running. This virtual machine is running in bridge adapter network mode, so my machine can run it. My machine is actually the Mac. Let me connect to it over SSH. I hope the screen is visible. Yeah, let me run. So this is Kitty terminal. I'll show you my terminal setup in a minute. So this is Kitty terminal, on which I have my custom Tmux configuration. That maybe I'll link in description, the link to that configuration file. But let me show you how Tmux looks on my system. So my setup is Kitty terminal because it is cross-platform. I can run it on any system. With that, I have Tmux as my terminal multiplexer, and my editor is Vim. So Kitty plus Tmux plus Vim. That is my thing. No Tmux service running. Let me run a new Tmux instance. Here you go. This is how it looks. Let me rename this pane as Kali. Let me SSH into, so let me see if this is also visible. Let me add this monitor as another system. So if I do this, now my Windows is visible. This is my Mac. And I'm also running Kali as virtual machine, so that should also be part of it. Let me add that. Screen might not be used that much. To know the IP, I'll do this. If config is running on 110, that's fine. Now what I'll do is that in order to ease our multiplexing, we will multiplex inside this already running Tmux session. For that, let me check if there is any session already running. No, there isn't. Here we go. This is the first session. Now I need to check what is the IP of Windows machine. Let me open command prompt here. Windows uses ipconfig instead of ifconfig. Let me check. It is running on 109. Okay. Let's try to ping 109 to see if we are able to connect to it. Yes, we are able to connect to it. And since we are running vulnserver, let us try to connect to it. That is running on port 9999. Let's see if we can connect to it. Yeah, we are able to connect to it. So I'll show you the logs of vulnserver there. So the request that we are sending, you can see it here. That it is accepting connections from 110. We actually access this. This is the logs that is running. So now let's try to fuzz it. So the point of doing fuzzing is that so what is fuzzing? Fuzzing means we are sending arbitrary input of arbitrary size to see if the software breaks, if it is able to handle any input given by the user. So that is the purpose of it. So if the software breaks, we try to figure out why it is breaking. And our prized result would be to find a buffer overflow vulnerability. So that is what we'll find. We'll use our custom script, a tool that I have written called gopher. We'll use that to fuzz. If we are able to break the software using fuzzing, we will check on Immunity Debugger, because our software is currently running inside of Debugger. Debugger is attached to it. We can see the trace to see how it crashed. So if we can figure out that yeah, it has crashed because of buffer overflow vulnerability, we will go ahead and exploit that. So let me try to fuzz it. So as you saw when we were doing netcat, I'm not able to connect to it. Let's see what happened. It seems to be running. Let me try to restart the server, vulnserver. To restart the server, what you can do is just click the back button. It will restart the server. Run it again and then again attach it to the debugger. Now let us try to run. It is showing running. Let's see if we can netcat to it. Yes, we can. So if I click help, you'll see these are the commands available. For the purpose of saving the time, let me tell you that this trun command actually has this vulnerability, this one, the trun. So we'll go ahead and test that, fuzz that. This is the way in which we'll fuzz it. So there is a gopher tool that I have already created and installed. So let me show you how you can install it. You go to github.com, you can search with my username Souvik Haldar, you'll get this tool. So this is the link to get this tool. Just as simple as github.com/SouvikHaldar/gopher. As easy as that. And you can install it using go get. So just do go get and then pass the command github.com. This. On your system, first of all have go installed. Once you have go installed, you can just do go get and then just paste this command. This will be used for installing. I'll add this in the readme so that it becomes easier, but you just execute this command and it should be installed on your system. Gopher should be installed on your system. Let me open another tab so that if I need to build anything, I can build it. I'll have this tab open. Now let us try to fuzz this. With I'll pass the IP of the target machine. This is actually 109 as we saw. The port is 9999 and the command is with C command trun. Actually, I have run this command earlier, so it was showing in autocomplete. So let's try to fuzz it. You see that it has crashed at 2100 bytes. Let us see the debugger. It should show that it has paused or terminated. So here you see that it has paused. Since we fuzz using this character A, you will see that this registers will be overwritten with this. So if you can see the top right, you will see that we ran the trun command with lots of A's. If you see the EAX register. Now our idea is to find the address of EIP. Let us try to find the address of EIP. So with this, just a second. So you can see that it has crashed. Let me disable this for some time. So you see that on the immunity debugger it shows that it has paused. So that is what we wanted to know, that by fuzzing a command we can get this state. It's an access violation. So that is good. We now know that this run command is vulnerable to buffer overflow, because it is showing that there is access violation when reading. That means that it doesn't know how to proceed next. Maybe the EIP, which is the that instruction pointer, doesn't know where to go next. Now we will try to find the EIP. So the idea is to control the EIP so that we can pass our arbitrary instructions there to execute. So we now know that it is crashed at 2100 bytes. So let us rerun the vulnserver so that we can try to find the EIP address now. That I'll show you in some time. Let us rerun it. For that you click the back button. Now it has reattached the software. Now let's click on play button to make it running. So now it shows that it is running. Now to find the EIP address, we'll use a command called offset. So all of it you can actually do by gopher help, and you'll know what are the commands available and all. For offset command also you can do the same thing. Let me try to get rid of this descriptions, because that is not what should be there. For offset also the same thing. This is actually boilerplate code that needs to be removed. I'm using Cobra package for creating the CLI. This is the Vim editor. Let me try to asynchronously run the compiler so that whenever there is a file change, it will run the go install command automatically. For that I am using this. Now whenever I'll run the save, go install will run. So again the same thing. We'll use the offset command, and with that you just pass the help tag and you can do it. So for offset, let me try to do the same thing. It needs to be passed I command for passing the IP, which is 192.168.0.109. The port is 9999. The command that we are trying to find the offset of is trun command. And now we need to pass the length at which we got the buffer overflow vulnerability from the previous step, which was 2100. At 2100 bytes it broke. So let's pass that number. Now you'll see that it is asking us to enter the value that we can see on Immunity Debugger for the register EIP. So if you pass this value, this tool can find out at what address does EIP register reside. So now if you go to Immunity Debugger, you'll see that it has crashed as we expected. Now if you see the EIP value which we need to pass, we'll just copy it, right click, copy selection to clipboard. Let us pass this value here, hit enter, and you'll see that EIP is found at address 2002. Now let us try to send some data to see that we are able to modify the value of the register. For that we'll use the send command that also you can figure out using help. So these are the payloads, the flags that you need to pass. Go for send the IP 192.168.0.109, the port 9999, the command for which you are able to do it, and now you can see that the A flag is used to provide the address of EIP. So the starting address of EIP, as we can see from the previous step, is 2002. Now let us try to pass a value at EIP. So let's send, since this is 32-bit machine, so you can pass 3 characters here, each of size 8. So we can use this 32-bit register. So we are trying to override EIP with CCCC, whose ASCII value is 43. So we should get the value of 43434343 in the EIP to know that we have been able to override the EIP. Let us check. So let me show you, for example, what is the value of EIP at this point in time. So the EIP value is this 69 whatever it is. So now with this command, let's see what is the value of EIP, what the value of EIP becomes. Let's rerun this program. Let us try rerunning it. This is reattached. Now let's try this play button so that it runs again. Now it shows that it is running. Now let's run this command. The idea is that at address, so if you see the end side of this command, you will see that we want at address 2002, which is the address, starting address of EIP, the value of CCCC, so that we will know that we are able to override. Let's run this command as usual. You'll see that it should have crashed. So yeah, it has crashed. And if you see the value of this register EIP, as we discussed, it is the value 43434343, 4 times C, and 43 is the ASCII value of C. So we are able to overwrite EIP. That's good. we have the control over EIP. Let us try to reattach it. At this point, actually, OBS is running, in virtual machine Windows is running, in virtual machine Kali is running, so all of it is running at the same time. My Mac is taking the hit. There is some issue, let me try to rerun it. Okay. I think it is ready to run. Yes, it is running. Let me try to netcat that in order to figure out that we are able to connect to it. Yes, we are. Okay. So now, okay. So now we know that run command is vulnerable to buffer overflow vulnerability. We did fuzzing in order to find out that it crashed at 2100 bytes. Then we found the offset. We used the offset command to find the address of EIP, because EIP is the one which holds the address of the next instruction to run, which is the place where we'll try to pass the address of our malicious program. So we were able to override the value of register with the value we want. That is fine. Now we need to see, because the idea is that we will pass the address of malicious program in EIP, which we can, but this malicious program has to stay somewhere. We'll put it in the stack, and the address of stack, starting address of stack is ESP. So now we need to figure out that can we put anything there, like whatever is our malicious code, can we put anything there? So this is the thing that we need to figure out now. So this step is called finding the bad characters, because every program has certain characters unique to it, so you cannot put anything there. So this is what we need to figure out. For that, we'll put all the hex characters there and in the ESP, which is the stack. Then we'll see that if everything looks the way it is in the immunity debugger. If there are certain characters which don't match, then we will try to not use those characters while building our malicious program. So that is the intent of this step. So let us send. So before that, let me show you. Again, open help. Yeah, so there is a register called ESP. There's a flag called ESP with which you can pass the values, anything there. If I pass 01, 02, 03, 05, this is the one that will get to the stack. So we'll know that is one of these 4 values bad or not for this program. Later we'll pass all the values there. So it has hopefully crashed. So now we saw that we ran this command to send 4C to the EIP register and this value as hex to ESP. So let's see how it looks on the debugger. So as usual, we have crashed the machine. The value of this register EIP is 434343 as we expected. Now in ESP, this is the starting address of the stack. Let's follow it in dump to see the values that we passed. So we see that in hex dump 01, 02, 03, 05. This is and the rest are the garbage ones that we haven't sent. So this is the value. So we see that there is no bad character among these four. So now let's send all the hex characters that is possible to figure out which character might be bad. This is actually an eye test. So let's rerun it. Now let's send all the characters possible, and all the characters you can actually find inside this repository. I have it set in the file called allhex.txt. So if you do this, you'll see that it lists all the hex characters possible, which start on 01, 02, 03, 09, then 0A, 0B, up to 0F, then 10, and all the values that are possible. So let me copy it. Copied all the values. Now this is what we'll use for sending. So instead of just these values, we'll actually paste all of it. So this is what the command looks. Enter. Let's see debugger. So the debugger has crashed. This is the register ESP. Let's follow it in dump. Now you can see all the values here, and you need to find out which looks funny. So it starts from 01, then it goes up to all the values. Then you need to actually figure out which one looks weird. Up to FF. FE, then FF. FE, then FF. So up to it, I don't think there is any weird looking value in hex dump. I'm just trying to increase the size. I forgot how to increase the size. I think here it is. So it seems, so let me try to follow this to see if there is any funny looking character. Zero 01, 03, 04, 06, 7, 8, 9, 0 A, B, C, D, E, F, and 10. Let me know if you can see anything, any weird character. We didn't send it from 00 because 00 is actually a bad character that is used for delimiting a string, I guess. .38, 39, then 3A. I'm not able to find any. So it should be like if 46 would have been a bad character, then you would see after 45 there would be something other than 46, then 47. That means 46 is actually bad character. Those are the values that we need to keep in mind to not use during creation of our payload. There is no value as such. F1, F3, then F9, then FA, FB, FF, up to it. So I think we are good to go. There are no bad characters. Next we will try to find, this is good up till now. So next we will try to find, is there any address in our current program memory status, our PCB, an address which says jump to stack, jump ESP, jump to stack. So if there is an instruction in our current program, then we will just pass the address of that instruction to our EIP. So when it comes to EIP, it will directly jump to stack, and stack is the place where we will pass the shellcode which will generate, excluding the bad characters that we might have found in this step. So this is the way it is. I'll cover it in the next video, the next part. Thanks for watching.